Hello everyone, in the lecture today we will go through more details about the computation in traverse terrain. The traverse computation is usually conducted on the plane coordinate, which is shown in the figure here. For the line in this coordinate, we will have the latitude and departure. If the y-axis is parallel to north-south direction, and the x-axis is parallel to east-west direction, then we can define the latitude as the north-south distance for the line, and the departure as the east-west distance. But we can also define the latitude and the departure based on general plane coordinates. Assuming that we have the line from point I to J, and we know the coordinate for these 2 points. At point I is xi, yi. Here xi is the horizontal distance from the point I to the y-axis, and yi is the vertical distance from the point I to x-axis. Similarly, we can find out the coordinates for the point J, which is xj, yj. Then the latitude can be defined as the distance along the y-axis, which would be yij equal to yj minus yi. And similarly, we can define the departure as the distance in x-axis, which would be xij equal to xj minus xi. The departure and the latitude of the line can be applied to estimate the azimuth of the line. Also, we can use the azimuth and the distance of the line to estimate the departure and the latitude. Assuming that aij is the azimuth of the line ij, and the dij is the distance of the line ij, then we can find the departure as xij equal to dij times sine aij. For the latitude, we have yj equal to dij times cosine aij. Also, we can find out the relationship between the departure and the latitude and the distance of the line, which is dij equal to the square root of xij square plus yij square. So with that, we can estimate the departure and latitude from the azimuth. Also, we are able to use the given coordinates and the departure to find out the coordinates of the other points in the line. For example, if we are given the coordinates of the point I and the departure xij, latitude yij, we can then find out the coordinates of the point J, which can be found from the two equations below. Xj equal to xi plus xij, yj equal to yi plus yij. Moreover, we are able to estimate the azimuth of the line based on the coordinates of the 2 points or the departure and the latitude of the line. For that estimation, we have the azimuth aij equal to the arctangent xj minus xi over yj minus yi is equivalent to the arctangent xij over yij, which is the departure over the latitude. If we are considering the specific case for n points from point 1, 2, 3, 4, 5, 6, we can also find out the relationship between the latitude from the start and end points and the latitude in between, and it will be similarly applied for the departure. For example, if we consider the general case n points, we can find out the difference between xn and x1 as the summation of I from 1 to n minus 1 xi I plus 1, and this term is actually the departure between the point I and I plus 1. Similarly, we will have yn minus y1 equal to the summation of I from 1 to n minus 1 for I plus 1, and this is the latitude for the point I and I plus 1. We need to use these two conditions to check the errors for the traverse based on these coordinates. In that sense, the traverse error is defined by the following two equations. For the error in the x coordinates, dx, it equals to xn minus x1 minus the departure for all the lines. That's from I equal to 1 to n minus 1, the departure I and I plus 1. For dy, we will have yn minus y1 minus the summation of I from 1 to n minus 1 latitudes of the line from I to I plus 1. This is the key concept we have to consider when we are using the plane coordinates for the traverse surveying. Now let's check one example to see how the computation is applied for traverse surveying. Here we will consider the closed traverse with angles to the right. And in the example, the initial and the final segments are given. So we know the azimuth of the initial line Q to 1 as A1, and the azimuth of the last segment phi to P as A5. In addition, we measure the angle to the right for all the points. With that, we have alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. And then we will see how we can apply the computation for this example. First, with the distance measurement, we can find out the distance of all the 4 lines, 1, 2, 2, 3, 3, 4, and 4, 5, which is shown in the second column. Also, we measure the angles at all the 5 points from 1 to 5, and the azimuth of the 2 initial and the final segments are given. We know that the precision of the distance measurement is 0.01 meter, and the angle measurement is 30 seconds. In the first step, we need to correct the errors in the direction measurement based on the method we proposed in the previous lecture. So in this experiment, we are given the azimuth of the first and last segment, and also we measured the angle to the right at all the 5 points. With that, we can find out the closure error as 1 minute, and then we can find out the correction for all the 5 angles. With this correction, we can then estimate the adjusted azimuth, and we will use this adjusted azimuth for the following computation. Next, we need to use the observed information and the estimated azimuth for the calculation of departure and latitude of all the lines, the coordinates of all the points, and the closure error. The table here shows the results from the computation. Basically, we are given the distance of all the lines, which is measured in the field experiment. Also, we have the adjusted azimuth from the previous page. In addition, we are provided with the true coordinates of the first point and the true coordinate of the last point. These true coordinates will be applied for us to identify the closure error. At first, we need to find out the departure and the latitude of all the 4 lines. With that, we need to call the equations xij equal to dij times sine aij. Dij here is the distance from the point I to j, and aij is the azimuth of the line ij. We also have the equation for departure. Yij equal to dij times cosine aij. With that, we can find out the departure and the latitude of all the 4 lines. And then based on the departure and the latitude, we can find out the coordinates with the initial coordinates of the point 1. For that, we need to call the formula xj equal to xi plus xij, and yj equal to yi plus yij. Then we can estimate the coordinates for point 2, 3, 4, and even 5. At the next step, we will try to identify the closure error. So we need to call the equation that we showed in the previous page. First, we want to find out the value of xm minus x1 and ym minus y1. For xm minus x1, which can be represented by the true coordinates at the point 5 and point 1, it will give us the value as 1297.839. Also, for the estimated value, there will be the summation of I from 1 to m minus 1 xi I plus 1, which is the summation of all the departure, and it will give you the value as 1297.542. This one will give you the error as 0.297. So that's the closure error for the departure. Similarly, we can find out the closure error for the latitude. We can find out the coordinate difference for the point 5 and 1, which will give you the value as 164.710. The estimated value will be the summation of all the latitudes, which is 164.514. With that, you can find out the error for the y coordinates as 0.196. So this would be the coordinates for the departure and the latitude. We also want to know the total closure error. So we have to call the formula here, dc equal to the square root of dx squared plus dy squared. With that one, we can find out the combined effects from the closure error at x and the closure error at y. For this example, the total closure error is 0.36. The closure error only tells you the absolute value of the error in the experiment. It does not tell you whether the error is large or small with respect to the total distance measured. In order to identify this relative error, we will introduce a new term, ratio of misclosure, ROM. ROM is estimated by the equation here, that is dc over d. Here dc is the total disclosure error, that is square root of dx squared plus dy squared. And d is the total distance measured, which is the summation of I equal to 1 to n minus 1 for di I plus 1. The computation can also be applied for closed loop traverse. The figure here shows one example about the closed loop traverse with azimuths, which means that we will estimate the distance of each side as well as the forward and backward azimuths of each side. This table summarizes the results from the closed loop traverse and the computation. From the experiment, we know the distance of each side, and also we can find out the azimuth of each line, which is the adjusted azimuth. And then we can calculate the departure and the latitude for each side as we showed in the previous page. With the given coordinates of the point 1, we can find out the coordinates of all the other points. As in the closed loop traverse, we will eventually go back to the point 1 again. So we can then compare the estimated coordinate of the point 1 and the true coordinate. With that, we can find out the closure error for x coordinate and y coordinate. For this example, it's minus 0.22 for dx and 0.17 for dy. Similarly, we can find out the total closure error as the square root of dx squared plus dy squared, which is 0.28 feet. From the previous pages, we computed the closure error for traverse. The next thing we want to handle is correct the error. This is called the traverse adjustment. Usually the adjustment is conducted based on the angular and the linear precisions. There are 3 conditions we have to apply for the adjustment. The first one is the condition when the precision in angles or directions exists is equivalent in linear distance. The second one is the precision in angle or direction is equal to its equivalent in linear distance. And last one is smaller than its equivalent in linear distance. In this class, we will only consider the second condition, and we will apply the compass rule for the traverse adjustment. In the compass rule, the corrections are applied to the departures and the latitudes directly. For the estimation of the correction, we first need to define several terms. Here, delta xi and delta yi is the corrections to the departure xi and the latitude yi. Delta xij is the correction to the departure xij. Delta yij is the correction to the latitude yij. Also, we have dxt as the total closure correction of the traverse in x-coordinates. dyt is the total closure correction in the y-coordinates. Li is the distance from the station I to the initial station, and L is the total length of the traverse. So they can actually be shown in the simple example here. This is the initial point, and this is the end point. We are considering the points in between. So Li as the distance from 1 to the point I, and L is the distance from 1 to point N. With that, we can find out the correction for the departure xi and the latitude yi. So delta xi equal to Li over L times dxt. Delta yi equal to Li over L times dyt. For the correction applied for the departure xi and the latitude yij, we will have delta xij equal to dij over L times dxt. Delta yij equal to dij over L times dyt. We will apply these corrections to find out the adjustment for the traverse with respect to the departure and the latitude and also the coordinates. Now let's check the previous example to see how we can apply the compass rule for the correction in departure and the latitude. From the previous example, we can find the total closure error as 0.36 meters. We also can find out dx is 0.297, dy is 0.196, and the value here is just the total closure error at the x-coordinate, and this one is the total closure error in y-coordinate. Also, we can find out the total length in the traverse as 1762.29 meters. Then we can use this information for the correction in departure and latitude. From the previous page, we get dxt equal to 0.297, dyt as 0.196, L is 1762.29 meters. First of all, we need to find out the distance of any points to the initial point, which will be shown in the first column here. This one, the first one, represents L2, and that would be L3, L4, and L5. Then let's see how we can calculate the correction for the departure. So for delta x2, it actually equals to L2 over L times d xt, which is 305.41 meters over the total distance as 1762.29 times dxt as 0.297, which will give you the value as 0.051. You can apply the same equation to find out all the other values. Similarly, you can find out the correction for the latitude. Say that if we are considering the first point, that is delta y4 equal to L4 over L times dyt, that is 1277.17 over 1762.29 times 0.196, which is 0.142. You can also apply the same procedure for all the other corrections. With that, you can find out the adjusted coordinates. For the first one, the station 1, we don't need to do any adjustment. While for the second one, based on the original coordinates that we estimated from the previous example, we can then add the correction to the original coordinates. With that, we can find out all the adjusted coordinates for the other 4 points, 2, 3, 4, and 5. With the adjusted coordinates for all the points, we also need to adjust the distance and azimuths for all the lines. With these two terms, we can actually apply the coordinates for the estimation of the adjusted distance and azimuths. For the adjusted distance, say that dij hat will equals to square root of xj hat minus xi hat square plus yj hat minus yi hat square. Here, x hat and y hat represents the adjusted departure and latitude. Similarly, for the azimuth, we have the adjusted azimuth as the arctangent xj hat minus xi hat over yj hat minus yi hat. Now let's see the example of the closed loop traverse to see how we can adjust the distance and azimuth. The table here shows the results from the observation and the traverse computation. We have the distance and the departure and the latitude calculated. Also, we find out the total closure error in x and the y coordinates and the total closure error. We can use this information for the adjustment about the coordinates. The table here shows the results for the correction. Here we will use the distance, departure, and the latitude of all the lines in this closed loop traverse. And then we will apply another equation for the correction of the departures and the latitudes. That is delta xij equal to dij over L times dxt. Delta yij equal to dij over L times dyt. You should know that the departure and the latitude here is different from the one in the previous example. Here the departure and the latitude represents the value for a line instead of on a single point. With these two equations below, we can find out the departure and latitude corrections. And then by adding the original departure with the correction, we can find out the adjusted departure and the latitudes. With the adjusted departure and the latitudes, we can then use the true coordinates of the first station to find out the coordinates of all the other points. Here you can see that the estimated coordinates of the station 1 is the same to the true value, which means the correction is applied correctly. And then we can apply the equations that we proposed previously for the adjustment of distance and azimuth, which will be shown in the figure on the right. So this would be the updated distance and azimuth based on the adjusted coordinates. So that's all about lecture today. Thank you very much for your attention. In the next lecture, we will introduce more contents in traverse computation.